have been discussing it over a period of time, and say you all know about the different states of matter, right? When we talk about the states of matter, there are by and large 3 states of matter that come to your mind. What are those? Solids, liquids, and gases. So you have solids, then you have liquids, and then you have gases. Right? Now in this there are primarily 2 features which are important and which distinguish all these 3 states of matter from each other, and those are forces of attraction and thermal energy. This I have already told you. Forces of attraction, when they are much higher than the thermal energy, then you have your solid state. When your thermal energy is much higher than the forces of attraction, then in that case you talk about the gaseous state. And remember that whenever we use the word therm, it's more or less related to heat. Alright, so if I am talking about thermal energy being greater, much greater than the forces of attraction, then it is this. And when we talk about liquids, then in that case the thermal energy is almost equivalent to the forces of attraction, or they may be just greater than or either a little less than each other. More or less, they like more or less the same. And there is a theory also that you know that in solids there is like a fixed pattern. They like fixed. There's a fixed volume, there's a definite shape. You know about those properties that you've been doing right from 8th grade. So when you talk in terms of solids, then in that case you know there are some particular features which are associated with solids itself. When you talk about gases, something that we'll be discussing in detail today, you know that gases have a very high volume. They have the highest compressibility, lowest density. We'll be discussing about all of them. But what about these liquids? Liquids actually have been, the properties of liquids have also been explained using Eyring theory of whole theory of liquids. There is a scientist with the name of Eyring, and he actually gave the whole theory of liquids, which stated that the properties of liquids are actually intermediate to those between or to those of solids and gases, which you already know. Basically what this theory states is that whatever property of liquid you talk about, if you have a solid and the gaseous state of matter existing for that particular system, then in that case the property will be an average of the solid plus the gases or gaseous property. Got it? So whatever property you talk about for liquids, it will nothing but be intermediate between those of the solid state and the gaseous state. This is basically what it talks about. Then after that, we can actually talk about the intermolecular forces that we've been talking of even before. But intermolecular forces basically are of 2 types. They can either be attractive or they can be repulsive. When we talk about the attractive forces, then in attractive forces we by and large talk about the van der Waals forces also. There are different types of attractive forces that we've already talked about, which actually combine your atoms to give you molecules and hold other subatomic entities together to form an atom and things like that. But by and large there are something which is like known as the van der Waals forces. Now remember that these van der Waals forces are also sometimes represented as London dispersion forces also. But remember that they are not the same. In fact, I have been iterative in telling you that van der Waals forces are nothing but they are a combination of different types of forces. And what are those different types of forces? Just a quick recap. We have, they are a combination of London or dispersion forces. They are like one and the same thing. They are sometimes called together also as London dispersion forces or London forces or dispersion forces. Then you have the ion dipole forces. You have dipole forces, and you have dipole induced dipole forces. Now for this case, to discuss about the very first one, in London dispersion forces, what do you have? Basically London dispersion forces exists in those atoms which are of the same size. which are absolutely identical and which are of the same size. So generally what happens is like they have the same size. So what causes some kind of an attraction between the two is like a temporary dipole which is created. In such kind of forces, a temporary dipole is kind of created. What happens, this temporary dipole, you know that the temporary dipole, what is a dipole? They are equal and opposite charges separated by a small distance. So this temporary dipole exists only for a short duration in order to make for these attractions to operate. And this works for the attractive forces between any two moieties which were otherwise not charged at all. So I mean, if I am putting, say these were like existing between any two systems which are of the same size, but some kind of an instantaneous or a temporary dipole will be created. So you can call it an instantaneous dipole also. An instantaneous dipole is created which actually makes for way for the attractive forces to operate. And such kind of attractive forces which act via the instantaneous dipole being created in otherwise non-polar systems are known as London dispersion forces. Then you know what are your ion, and remember that in all these cases the interaction energy for the London dispersion forces is inversely proportional to r to the power 6. The interaction energy is inversely proportional to r to the power 6. This is asked many a times in the entrance examinations also. So please keep this figure into consideration. Then after talking about these London dispersion forces, we come on to the next type of forces which are like the ion and dipole forces. This is like you already have some kind of a dipole in the form of a solution or a dipole existing, and you're introducing an ion to it. So if in case you say your Na plus is interacting with water, if your Na plus is interacting with water, this is some kind of a dipole which is there. Right? If Na plus is interacting with this will be called as the ion dipole interaction. Alright? So any kind of an ion, see when you know all salts are strong electrolytes. Did I tell you that? Remember, this is like a thumb rule that you have all salts are 100% or strong electrolytes. What are strong electrolytes? Strong electrolytes are those which dissociate completely on dissolving in the aqueous media. Strong electrolytes are those which get dissociated. Dissociated means broken down into completely in its own ions on getting dissolved in aqueous media. Like for example, HCl is a strong electrolyte, but it's not a salt. I'm just giving you an example. If HCl is a strong electrolyte, it will dissociate into H plus and Cl minus. Now if I talk about any salt, what salt? NaCl, that is a strong electrolyte, means that the moment it is dissolved in water, it will completely get dissociated into Na plus and Cl minus. If I talk about say KNO3, it is K plus NO3 minus. Again it's a salt which will get dissociated completely. When I say strong electrolyte means it will completely get dissociated and the original identity of the molecule will be lost. That's fine. So ion dipole forces are like, say when you dissolve salt in water, so you know that ions will be independent, Na plus will be independent, Cl minus would be independent, and both of which will be interacting with what? The solvent molecules, which are some kind of a dipole. So in such case you can say that this is an interaction between an ion and a dipole. Then next we talk about the dipole forces, and you know dipole forces can operate between molecules like HCl, where you have a delta plus delta negative charge, and this can interact with another one which has a delta positive and delta negative charge. So this is some kind of a dipole interaction, and in this case of dipole interaction, remember that the interaction energy is inversely proportional to a factor of r to the power 3. For the dipole forces, remember that the interaction energy is inversely proportional to 1 upon r to the power 3, where r is basically the distance between the two dipoles that we are talking about. Okay. Then we talk about the dipole-induced dipole. Dipole-induced dipole would be the case where you bring an already existing, I've written it in short form, when we talk about dipole, induced dipole forces, then in that case we talk about bringing a dipole like A plus B minus in the close proximity of another molecule which is non-polar. Polar means what? Whenever there is a charge separation, you call it a polar molecule. Non-polar means what? There is no charge separation at all. So whenever, and if this is polar means it has a dipole, and the dipole is always facing towards, the dipole vector is always facing towards the more electronegative element. So in this case, we are just talking about the dipole interaction. When a dipole interacts with a non-polar molecule and it comes into close proximity, then it induces some kind of a charge in the close proximity like this. The one which is like positive will induce a charge into the non-polar molecule such that the negative charge will be developed on the nearer end and the positive charge will be developed on the farther end. So that way this initially did not have any dipole existing. So that is why this will be called as an induced dipole and this will be called as the original dipole. And whenever you have such a case, you say that it is a dipole induced dipole interaction. And again in this case, the interaction energy will be inversely proportional to r to the power 6. I'll repeat it again. See, the last thing I'm saying that first of all we are talking about the intermolecular forces. Intermolecular forces means the interaction of one molecule with another molecule. It may be the same one, it may be some separate one, it may be anything else, but with a different molecule. So in that I'm saying that in attractive forces by and large we talk about the van der Waals forces to begin with. Van der Waals forces are simple forces which are simple attractive forces only. Understand it like that. They are nothing but they are a combination of all these forces together. You have London or dispersion forces, you have ion dipole forces, you have dipole forces and you have dipole induced dipole forces. When you talk about London forces, remember that the interacting systems are of the same size. So if you have any molecule, they will be of the same size. And then how do they attract each other if they're like not having anything like a dipole or any charges? In that case what happens, both of which, if both of them do not have any charge on it, then in that case they develop some kind of an instantaneous dipole. So remember just this, that how do London dispersion forces act as an attractive force? By creating an instantaneous dipole. That is like a temporary kind of a dipole which is created, which holds the molecules. They are like the weakest of all. And that is why the interaction energy is inversely proportional to r to the power 6. Then next I talked about the ion dipole forces. Ion dipole forces are like, how do you create ion? Because ions as it is are very difficult to exist in the gaseous state. If you have to get an ion in your hand, it's like not easy. So in that case you need to have a molecule, you put it in water, and that is why I introduced you to the concept of water strong electrolyte. So you take up any salt, put it in water, it will get dissociated into its respective ions. So now say if you are putting NaCl in water, then Na plus reacts with the dipole created by water. So that's an ion and a dipole interaction. So that is called as an ion dipole force. Then when we talk about dipole forces, you can take up any dipole which has any polar molecule interacting with another polar molecule, because that's one dipole interacting with another dipole. Then last one, that is dipole induced dipole forces. In that we are talking about the interaction of an already existing system which is like A plus and B minus. So this is some kind of a dipole. In fact, they are all represented by a sign of delta. This delta represents partial charges. Let me just tell you one thing here, right here. See, whenever I talk about the breaking of the bond, remember we've already done something like this. Whenever I talk about the breaking of the bond, then in that case, you know, if this is shifting the bond to the B completely, तो दे कौन रहा है? E. So it will become A positive and B will become negative. So we put a positive and a negative only after complete shifting of the bond. Now here in this case, if I am saying B is more electronegative and A is electropositive, then in that case the bond has not broken yet. So electronegative atom has a tendency to pull the electron density towards itself. So it will pull the electron density, so that is why we represent it by a partial charge. That means it has not taken up the bond completely towards itself, it has not taken up the electrons totally towards itself, but rather till the bond remains intact, you represent it only with a partial charge. And so is the case with A, it becomes partially positive. So this is how you generally represent. Alright, so when I am representing dipole with a plus minus, please understand that I am talking about only partial charges. So you have a dipole created here. Whenever you get this dipole near, say, a non-polar system which has no charge separation, then in that case what will it do? This positive charge, as soon as it comes in contact with a non-polar, which is also made up of electrons, then it is develop some kind of a negative charge near the end which is towards the positive of the other. So this, if this gets negative, the other has definitely shifted some charge towards it. So then this will develop a positive at the farther end. So what happens? This is some kind of a dipole which has been induced. It was not already existing, but rather it has been induced due to the inductive effect coming from the polar molecule. Right? So that is why such an interaction is known as dipole-induced dipole interaction. And when you take a sum of all the interactive forces that we talk about, then it lands up to give you van der Waals forces. Then it forms van der Waals forces. Clear? Then here, let's now talk about some things which are like related to London dispersion forces also. Remember that with increase in the number of electrons, this London dispersion forces increases, and also with increase in size, molecular size. With increase in molecular size, again London dispersion forces increase. Yes, you can say that. Whenever there is no other operative action which is operative, then you say that London dispersion forces are definitely operative for it to be a stable system. Dipole-induced dipole will act as long as the induced dipole remains intact, till you bring about some kind of a separation between the two molecules. Okay, and remember that if I talk about say HCl system is what I did talk about. If I talk about HCl, what kind of an interactive force will you talk about here? Dipole-dipole. But here let me tell you, whenever we talk of a dipole-dipole, also remember that here we can talk about hydrogen bonding also, but we do not talk about hydrogen bonded forces as the van der Waals forces ever. That is because the magnitude of the hydrogen bonding is so different that it is taken as a separate class apart from the van der Waals forces. Remember that hydrogen bond is what? It is a bond formed between hydrogen and an electronegative element. So in that case, this will be the hydrogen bonding case wherein a dipole is interacting with dipole. So you can say that hydrogen bonded forces are a special class of dipole-dipole forces. Alright. Next, let us quickly discuss the properties of gaseous state ones. What we are going to do in this particular topic is to talk about the gaseous states of matter in detail. Some properties of gaseous state that you've already done so many a times before are like, the very first thing is like we do say that thermal energies is very higher, very much higher than the forces of attraction. Then the second thing that we talk about is, now what happens in case of gases? You know, the molecules are free to move. They're absolutely free to move. So the volume is the highest in case of gases. If the volume is the highest, then in that case density is equal to mass upon volume. So if volume is really high for gases, then in that case the density will be the lowest. In fact, density will be the lowest of all three states of matter. So remember that they have the lowest density. Then third, you know that they do not have any fixed shape, or these are like something that you've already done in the lower grades, maybe 8th or somewhere, no fixed volume or shape. And then remember that they exert equal pressure in all the directions. They exert equal pressure in all directions. What does the last statement mean? I am talking about the gaseous state, And the last property that I'm talking about here is that they exert equal pressure in all the directions. Please remember that if you actually have to find out the pressure of the gas, we all are surrounded by a gas. In fact, air is nothing but a gaseous mixture, right? If we have to find out the pressure of the gas right here, right now, how do we have to actually find out? You will realize the pressure of the gas or any gaseous mixture only when the molecules of the gas collide with something, right? How will you actually say that there's a lot of pressure here? Only when it collides with probably your uh, say facial features or something, I mean with face or something. But remember, now it's like kind of a thumb rule that you have to remember, that the pressure of the gas is mainly due to the collision of the gaseous molecules with generally the sides of the container. Say if I have to talk about the pressure of the gas will be only due to the collision of the gaseous molecule with some hard surface. So that is how pressure is actually created. So remember that the pressure of the gas is always due to the collision of the gaseous molecules. In general, whenever we perform an experiment, the pressure is due to the collision of the gaseous molecules with the sides of the container. And when I say that the pressure is like the same in all the directions, if I am saying that the pressure of the gas is same in all the directions, then in that case I mean to say that it is equal in all directions without any bias. So if this is a gaseous molecule, the pressure that is created will be like the same in all directions. So that is it. And now when we talk about the periodic table, I am in particular talking about just the gaseous state, remember that. Now, when I talk about the periodic table, you know that each of the elements may exist in some or the other kind of states of matter. Then how many elements in the periodic table exist in the form of gases? 11. 11 elements exist as gases. And what are those? I'll just quickly put it down and you can remember them also. Hydrogen, nitrogen, oxygen, fluorine and chlorine. Hydrogen, nitrogen, oxygen, fluorine and chlorine. And then you tell me which gases do we talk about. Now that we've done periodic table, there is one particular group which is generally known as gases only. What are those? Noble gases. Noble gases. What are those noble gases? Helium, neon, argon, krypton and xenon and radon. So 11 done. Yeah. So remember that out of all the periodic table elements, there are 11 which exist in nature in the form of gas. And they are hydrogen, nitrogen, oxygen, fluorine, chlorine and then all the noble gases that you remember. Then let's talk about the measurable properties of gaseous state. Let's talk about the measurable properties of gaseous state. The measurable properties of gaseous state would be, first we talk about the mass of the gas, and the mass of the gas can be generally seen in grams or kilograms. The mass of the gas will always be generally seen in grams or kilograms. Next we can also talk about, say, volume. Now the volume of the gas will be the volume of the container. So in that case, the volume of the container, remember that the volume of the gas will always be equal to the volume of the container. And please remember the general conversion units. In this chapter you will have a lot of numericals which will be directly straightforward. So you do not have to really worry about them. All the values will be given, you just have to substitute and get the answer. 1 liter you know is equal to 1000 milliliter. That will be equal to 1000 centimeter cube, which will be equal to 1 decimeter cube. So now there is one thing. Whenever you talk of liter and decimeter cube, that's one and the same. And remember that whenever you talk of centimeter cube and milliliter, that's one and the same. Will you remember that? Because this is really very important. Whenever you talk about the conversion, 1 liter will be equal to 1 decimeter cube, which means that you can talk about liter or decimeter cube in terms of the same values. And then you have 1000 milliliter and 1000 centimeter cube is equal to 1 liter, which means that your centimeter cube and your milliliter, they can actually match up with one another. Also, then if I talk about the conversion of 1 meter cube, then your 1 meter cube will be equal to 10 to the power 3 decimeter cube. If 1 meter cube is equal to 10 to the power 3 decimeter cube, then that will also be equal to 10 to the power 3 liters, which will be equal to 10 to the power 6 milliliters, which will be equal to 10 to the power 6 centimeter cube. So remember that this is another thing that you have to remember, the conversion factors. 1 liter is equal to 1000 milliliter, which is equal to 1000 centimeter cube, which is equal to 1 decimeter cube, because sometimes the values are given in decimeter cubes and you keep wondering how do you have to convert it or use it like that. Another thing is like 1 meter cube is equal to, then if you know how to convert meter to decimeter, I hope all of you all remember kilometer, hectometer, decameter, meter, decimeter, centimeter, millimeter, and that the same units go for liter and other things also. I am not taking up a small grade of mathematics here. So this is another. Next we can talk about the measurement of pressure. Remember that for gaseous pressure the instrument used is manometer, and for atmospheric pressure it is barometer. So please remember that for the measurement of pressure you have the gaseous pressure and you have the atmospheric pressure. For the gaseous pressure we use manometer, and for the atmospheric pressure we use the barometer. Another thing that I wanted to state is, like I saw a question based on this, whenever you have an open end manometer, then in that case the pressure of the gas is equal to the pressure of atmosphere minus H. And if it is a closed end, just in case if you get a numerical based on it, and if it is a closed end manometer, then in that case the pressure of the gas is equal to H, where H is the difference in the mercury levels in the two columns of densities. H is nothing but it is the difference in the mercury levels in the two columns which were set up to measure densities, set up for densities. So remember this, that for the pressure measurements, and pressure is a very important, there are generally three variables for gaseous state, which are pressure, volume, temperature. All these three variables are something which need to be defined for your gaseous state completely, unless and until you keep one of them constant. Okay, another property is that of temperature. We've talked about mass, we've talked about volume, we've talked about pressure, and now let's talk about temperature. Temperature can either be measured in degrees Celsius or in Kelvin. All of you all are aware of that. And when you talk about the temperature in Kelvin is generally taken in the SI units. So whenever you talk of temperature in Kelvin, you know how do you relate it to temperature in degrees Celsius? That is T degrees Celsius plus 273.15. This T will be in degrees Celsius, say. Then in that case, when you add it to 273.15 Kelvin, then you get your answer in Kelvin. The temperature in Kelvin is nothing but 273.15. We'll also discuss as to how it was like introduced. Then there is one condition, that is condition of standard temperature and pressure. The standard temperature that is taken is 273.15 Kelvin, which is nothing but 0, which is known as the absolute 0 or 0 degrees Celsius. Now this 273.15 along with 1 bar pressure, and you know that 1 bar pressure is nothing but equivalent to 10 to the power 5 pascals. So the molar volume of an ideal gas at STP is equal to, and you know that the molar volume at STP is equal to 22. 22.4, 24, 22.7. I just found it is 22.7. Okay. So now the molar volume at STP. Now there is another condition which is sometimes referred to in numerical problems, which is standard ambient temperature and pressure. If this is your STP or NTP is considered to be the same. STP is your standard temperature pressure, NTP is your normal temperature pressure that you take as 0 degree Celsius and 1 bar pressure. Now here in case of standard ambient temperature and pressure, your temperature is taken as 25 degrees Celsius, which is normally the room temperature. Please remember that. In this case, your temperature is taken as 25 degrees Celsius, which is the normal room temperature. That is, the temperature is taken as 298.15 Kelvin. I just simply add 25 to it and 1 bar pressure, and then your molar volume is equal to 24.789. Molar volume at SATP conditions is equal to 24.789. Temperature and pressure. That's normally the room temperature and pressure. Your normal atmospheric pressure at the present case will also be taken as 25 degrees Celsius and the pressure will be taken as 1 bar. Then there are certain set of laws which actually define and help us in understanding the properties of gaseous state. Let us look into those laws. By and large, I'll just give you a preview of what we are going to do. We are discussing gaseous state and the properties have already been discussed. One of the most important properties that I stated is your pressure. And how do you actually define your pressure? Pressure will be obtained, or pressure of any gas is by the virtue of the collision of the gaseous molecules with the walls of the container. Alright, one thing is that. Another thing is like this pressure has dependency on volume as well as temperature, or the other way around. Volume has dependency on pressure and temperature has dependency on pressure and volume. Now all these three entities that I talked about, that is pressure, volume and temperature, can be discussed. All these things are important. Along with that, something that you've already done is like, unless and until you define the amount of any system, it becomes incomplete. So to define the amount of system, we use the number of moles, which is small n. So now four things that we are going to discuss now is like n, which is the amount, then T is the temperature of the gas, P pressure and V volume of the gas. Now for that, I will have a certain rules or laws to define. So this is just a preview. I'll start with Boyle's law, then we'll move on to Charles' law. You have Boyle's law, Charles' law, and you have Gay-Lussac's law, and you have the Avogadro's law. And when you combine the first three, you can easily get the ideal gas law. That is the ideal gas law. Now when you talk about the Boyle's law, remember that temperature is constant. When you talk about the Charles' law, remember that pressure is constant. When we talk about Gay-Lussac's law, volume is constant. Why am I telling you right initially? So that you immediately remember this, that whenever you talk of Boyle as the name suggests also may be linked to temperature. So remember that for Boyle's law, temperature will be held a constant. Then the second is Charles' law. For Charles' law, remember that pressure will be a constant. Then for Gay-Lussac's law, you will have volume as a constant. And then when you talk about the Avogadro's law, it defines that for 1 mole you have a fixed number of atoms, molecules or ions, and that is your Avogadro's number, which is 6.022 into 10 to the power 23. That you've already done. And when you combine all these, then you get the ideal gas. Now let's discuss the first one, which is the Boyle's law. Boyle's law, please memorize this right here, right now, that Boyle's law is for constant temperature, Charles' law is for constant pressure, and Gay-Lussac's law is of volumes. Okay, so now when I talk about the constant temperature, let me just tell you that Boyle all these 3 laws, I mean 4 or 5 laws that you're going to do are named after the name of the scientist who actually worked with them. And normally what is done is like they take a particular container. How are these experiments performed? How do you actually come down to these laws? What do they do is like they take up a container and fix up a certain volume of gas in it. Alright, then they'll study what happens on increasing the pressure. If on increasing the pressure volume is decreasing, then in that case they will say that the pressure is inversely proportional to the volume. And what is done is like not just one set but many sets. Say for example, if I am taking up a gas in a container, what will be happen fixed with a movable piston. Now if I am increasing say pressure 1, the volume initially was V1. Then all these values will be noted down. When the pressure is 2, it will be noted that the pressure has increased and the volume will decrease, say if P2 comes down. Then again there would be another set P3 which will have a volume of V3, and then the relationship was studied. In all these cases it was found that as the pressure increased, your volume decreased. So Boyle's law states that at constant temperature your pressure is inversely proportional to volume. So volume will be taken in the denominator. And whenever you remove the proportionality sign, you know that you get a constant associated with it, that is P is equal to K1V. Now what do you have to do with it? In this case, say for example, if I have to make a plot of P versus V generally, if I have to make a plot of P versus V, then you know that as volume increases, as pressure decreases, your volume will increase. As your pressure, say I talk about a high pressure, the volume will be very less. Alright, say this is the first observation point. Then I reduce the pressure a little, then the volume will increase. So on, and all these points can be plotted. So then in that case I get a curve which looks something like this. Is that clear? This is like a simple mathematical curve based on the expression that we got. Boyle stated that pressure is inversely proportional to volume, because of which we get this is in fact obtained from the plot. Because what happens is at say pressure P1, volume was noted as this. When the pressure increased, then again the volume was noted. Then when the pressure is increased further, then a corresponding volume. So x and y values are obtained like that, and then on joining you get a curve. And then you obtain the relationship of the curve which says that it is inversely proportional. Now if I have say more graphs associated with it, you know what is this? In all these cases you have temperature as constant, and whenever you draw a curve or a plot at a constant temperature, it is known as an isotherm. It is known as an isotherm. Isotherms, iso means same, constant, and therm is related to your temperature. So constant temperature graphs are known as isotherms. Now here if I have T1, T2 and T3, you get such questions in the examination also. You will be given a number of plots. So it is all on your basic understanding of just this expression. You know that first of all go through the graph. The graph is like proper. As volume is increasing, your pressure is decreasing. That goes hand in hand with your Boyle's law. That's okay. Now if you have to tell that which is the correct order for temperature, say T3 is greater than T2 is greater than T1, then second T3 is less than T2 is less than T1, then another case you can have T3 less than T2 greater than T1, and the fourth case may be none of these for all reasons. Alright? Do not get tempted by all of these or none of these, because many students have the tendency of not going into the question and rather marking these, and this may be one of the answers which is like not correct, because in many cases it happens. So remember that whenever I am talking about this, now if you have to find out about temperature, just use your simple logic. You know that for a particular temperature, for a particular pressure, you can easily find out the different volumes. Say I am like messed up a little. Look into the graph. I am just telling you that you can apply your common sense on your own. Any new question can come up from the plots based on your simple understanding. You have 3 graphs given. You are given 3 temperatures also. you have to tell the order of temperature, that which may be the highest or which may be the lowest. It is not possible to mug up all the plots. So what you do is at a particular pressure, एक pressure पे एक constant line बना लो. So this is like a particular pressure. Now just check out that volume is less here, volume is more here, volume is the highest in case of T3. And when do you think? When the temperature is high, you know that the molecules will be in random motion. So there will be a little, there will be large volume for that case. So then in that case, what do you think? T3 will be the highest, followed by T2, followed by T1. So in that case, the first option. Did you get it? You can actually apply this logic, because this trend of temperatures or pressures as we move on to the other laws will definitely come. And it is a simple logic. Understood? So remember that Boyle's law states that at constant temperature, the pressure of a gas is inversely proportional to the volume of the gas. And when you remove the proportionality constant, you of course get a constant. When you remove the proportionality sign, you get a proportionality constant, which will be K. And based on that, you can actually draw a graph now. Now, similarly, you can have more plots also. Let's take up the Boyle's law in detail then. There can be more plots also which are possible. Say now, if I take pressure to be as K1 into 1 by V. This is what it is. Pressure is equal to K1V. I can take this pressure to be equal to Y is equal to M into X. If I plot a graph between pressure on the y-axis and 1 by V on the x-axis, then in that case, what is this equation of? It is the equation of a straight line passing through the origin. Why? Because otherwise, what is the equation of straight line? Y is equal to mx plus c. Where if c is 0, then in that case, you know that the straight line is passing through the origin. So in this case, here P I have taken on the y-axis, I have taken 1 by V on my x-axis. So naturally, I will have the constant coming in from the slope of the equation which is passing through a straight line. So this will be the relationship, and the plot will look something like this, right? Again, for this case also you can have different slopes, and you can apply your logic accordingly. Say this is T3, T2 and T1. Now one by one again. I have used the same T1, T2, T3 so that you can understand. Now again, for any range you can just drop in. If you again have to tell, I give the same options again. You have to tell the order of temperatures for the 3 slopes which are given. You have to tell the order of temperature for the 3 curves which are given onto the graph. First of all, you will be checking which of the plots is giving the correct graph. Correct graph is obtained from all, because your pressure and 1 by V will give you a straight line with a passing through the origin. So in this case again, if I draw a line which is parallel to my x-axis, then in that case, you know that when the temperature is high, my volume will be very high. If temperature is high for a given pressure, if temperature is high, you know that there will be random motions, there will be more volume. If volume is high, then your 1 by V will be less. So following that pattern, again 1. So just think with a cool mind and you will be able to answer. So you can have more plots also. Like again from this relationship only, P is equal to K1V. Let's take the log, because in your x and y axis, and remember that there whenever you draw a plot, because sometimes in your subjective paper also you are asked to plot how the P versus 1 by V looks like for a particular gas at constant temperature. So you know that you have to plot the isotherm. So you will straight away draw a line like this, and then the teacher will give you a 0. Why? Even if the plot is correct, how do you know that this P stands for a Pepsi or stands for the pressure? You have to actually signify you write down the general P and you write down your 1 by V, but unless and until you specify your axis, label your axis, it is meaningless. Because how do I know that this plot is between your height or weight, or if it is between pressure or volume, or if it is between log P or log V. So nothing is clear till you label your axis. So do not go and argue with your teachers once if you've not yourself labeled the axis. It is very important for each of your plots to be labeled absolutely correctly. So make sure that you write it down carefully, because with change of the labels you get the change of the graph entirely. So make sure that you label them correctly. Now again, Boyle's law is equal to P is equal to K1V. Now here if you take the log, what will it become? Log P is equal to, P is equal to K1 by V is our Boyle's law. So that is log P is equal to log K1 minus log of V. यही बोल रहे थे? नहीं. तो log V. Alright, now you make the graph between log P versus log V quickly. All of you all make the graph between log P or log. Why PV graph is not a straight line? For constant T. For a constant T it is a straight line only. P by V. That is like, it is like an inverse relationship. This is like all based on the set of observations. Let me just tell you, there is one thing which is absolutely clear, that when Boyle performed his experiments, there were certain set of data for P and V which were correspondingly noted, and then you actually get this relationship. And remember that here when you are talking about P by V, it's kind of an inverse relationship. And it becomes linear only when you have a relationship which goes in mathematically as good as the straight line graph. Right? Yes.
Can we do like that? On pressure we draw line and then
Yes, if you keep the volume constant and then you find out pressure, yes, equal thing will go on. Right?
in that case it will be like V1 will be at lowest.
Say no, if you keeping this as, say here only, let's check it out here. Say let's keep the volume now constant. Alright. Now here, when the temperature is high, let me tell you, if the temperature is high, what will happen? The molecules will move. The molecules will move rapidly. Don't take it like that. When the molecules will move rapidly, then what will happen? There will be more collisions. So in that case, so that is how. Okay. So now here when we talk about log P and log V, what is now this equation? Let's look into this equation also. This is like y is equal to, say I have plotted your log P versus log V. So this is kind of, this is your x, right? Say mx plus c. So in this case you will get an intercept also. The intercept will be corresponding to the value of log k1, and because your slope is negative in this case, what is your slope? -1. So in this case your slope will be this. So the graph will look something like this in this case. Log P versus log V will be a graph that looks something like this. Alright, let me just revise the plots once again. Boyle's law states that at constant temperature, as the name suggests, Boyle, so at constant temperature, remember that your pressure is inversely proportional to volume. Now if pressure is inversely proportional to volume, the clear-cut relationship P is equal to K1 by V. Any K, it's up to you, K1 by V is what I am calling it. Then if it is K1 by V, we plot a graph between P and V, you know it's an inverse relationship. As pressure is decreasing, your volume will increase, or the other, or vice versa. So now for that I have just told you that there can be different plots which are possible at different temperature. Each of these curves is known as your isotherm. All these plots are nothing but your isotherms. Whatever plot is made at a constant temperature is known as an isotherm. So now here, if I have to check out the relationship between the temperatures for different curves that I have plotted, what will I do? I will just apply a normal logic, draw a constant, take any particular pressure or any particular volume, and then just understand the qualitative relationship as per your understanding, and you will get to know easily that the ratio in, that the order in this particular case will be T3 is greater than T2 is greater than T1. Alright, then another case, you can have a graph also between P versus 1 by V. We'll have a graph of P versus 1 by V, and this graph will be similar to a straight line passing through the origin. This is y is equal to mx plus c. So now in this case your proportionality constant will be obtained from the slope, and it is nothing but a straight line passing through the origin. So in this case again you can have different isotherms. The basic graph that you actually draw, if you have to draw a graph between P and 1 by V, is simply this. But because you will have many questions based on plots, so that is why I taken up that you can have different plots, and given that the temperatures. Let me tell you, the book, the very good book that you are referring to, NCERT, has the temperature values mentioned. But it is not feasible to remember all the temperature values. So you should rather remember the trend, and remember the logic behind that trend also. Now here this was P versus 1 by V, and this is a straight line passing through the origin. You know why? From the relationship itself. And when you check up for your relationship, you can easily say that now after drawing the line, straight lines, which temperature will be higher? T3 will be greater than T2 will be greater than T1, and so was the case in the other one. But remember that the order will be, if I write it like this now, T1, T2 and T3, T1 greater than T2 greater than T3. Please remember, because some students still now also have the habit of just remembering things and doing it like that. Do not do that. Then the next thing is, I also told you that you can also draw a plot in many other ways which are possible by altering the mathematical relationships, and one of which can be like you take the log for this relationship of your Boyle's expression, that is P is equal to K1 by V. What will be that expression? That will be log of P will be equal to log of K1 plus log of 1 by V, and you know that log of 1 by V can be written as minus log V. So this is like clear to everyone. This is an equation of a straight line. If I actually plot a graph between log P versus log V, if I plot a straight line of log P versus log V, then in that case, you know, this is like some kind of a relationship which is of a straight line with an intercept. Y is equal to mx plus c. And here in this case, my intercept will be my log K1, whatever intercept is made on the y-axis. And now what will happen? Will it be a straight line with a negative slope or straight line with a positive slope? Will be decided by the coefficient which is here. What is the coefficient here? Minus 1. So in this case, that means I will get a straight line, because this is an equation of a straight line. I will get a straight line with a negative slope. So the graph will look something like this. Okay?
Can we join this line with the x-axis?
See, in that case, I'll tell you there are many hypothetical cases also, as you can have log P, if you can have log P going on to become almost 0, then you can limit out on the value of volume. And those values and temperature, pressure and volumes will be discussed very soon when we talk about critical temperature, critical volumes and so on. So it is better to just leave it like that. Like here also you are talking about low pressures, you are talking about the, say when you talk about P versus V, if you talk about this is almost reaching up the volume of the gas to be almost going to infinite here in this case, right? And when you are approaching to this side, your pressure is very high at very low volumes, which means that your volumes are almost approaching 0. And when will the volume of the gas become almost equal to 0? When it is almost liquefying. When will the volume of the gas become? So those are like the final extreme cases that we'll discuss. Okay. So now with this, I think Boyle's law is completely discussed, and if you've understood the graphs, the various graphs that we've plotted using the Boyle's law, then I think for the rest of the laws it becomes easy, because you will have graphs for the other cases as well. A repetition of one of the laws that we did, one is like, the very first law that we've done is Boyle's law. It is noted down at constant temperature, and it states that your pressure of the gas is inversely proportional to the volume. Remember that there can be many plots that can be plotted, and you can find out the values also dependent upon them. And now we move on to the next law, which is Charles' law. Before we move on to the Charles law, I'd like to just talk about one more thing about Boyle's law. I stated that this is your Boyle law, Boyle's law, right? This is your Boyle's law, that P is inversely proportional to volume, that is P is equal to K1 by V, which means that P into V is equal to a constant. So remember from here that PV is equal to a constant. That means if I start up with my reaction, then with my say experiment, then say the initial pressure, if it was P1 and initial volume was V1, then the final pressure and final volume attained will also be equal to the same value, that will be equal to P2 into V2. Please remember, this will be used for the numericals, that P1 V1 is equal to P2 V2. P1 V1 is equal to P2 V2, because this is also Boyle's law. PV is equal to a constant is your Boyle's law. Then now we move on to the Charles law. Charles law is at constant pressure. And what Charles noted, can we talk about different values of temperatures for log plots? Yes, then in that case, again you will have to apply your logic, but then you will have to relate it to your log and then anti-log values. Generally such questions are not asked, but you should be able to tackle them as well, depending upon the log and the anti-log pattern. So we're not going into the details of that, we'll just go through the questions of the previous year's papers as they come. But majority of the cases it is a direct applications of your mind where you can apply your logic easily. So never the questions are like that where you have to actually sit down for a minute or two. So now next we move on to Charles law, and for Boyle's law I've already told you that before, what did I state? The last thing that I stated for Boyle's law was PV is equal to a constant. So remember, this is one thing that is to be noted. And now another thing is that note that as pressure increases, what will happen if pressure increases? Volume decreases. If volume decreases, what will happen to the density factor? What is density equal to? It is mass by volume. So density will increase. Alright, now here, if density is equal to mass by volume, I can also get another relationship. What is your volume equal to? Volume is equal to K1 by P. Volume is equal to K1 by P. Clear with it? So in that case, I can also state that my density is directly proportional to pressure, because this was the question that was put. Remember that we can even relate it to other properties. I am still on the Boyle's law. The last thing that I am talking about Boyle's law is that we know that PV is equal to a constant is like absolutely clear. Now we know that from a qualitative understanding. What is qualitative understanding? Whenever you do not go into the mathematics of it and understand it logically. So what we have is, if your pressure is increasing, volume is decreasing. That is even from your Boyle's law. And when volume decreases, density will increase. If density will increase, we can directly relate it. Now also mathematically the same thing. How can you relate it? That means your density and pressure are related. In both the cases I am saying density increases when volume decreases. So how can you relate it? How you can relate it like density is equal to mass by volume. What is your volume? Volume is equal to K1 by P from your Boyle's law, and this implies that your density is directly proportional to pressure. So whatever will happen to the pressure will also happen to the density. This was another thing that I wanted to do. Okay, now finally the Charles law. Next law. Charles law, we talk about constant pressure. And remember that even in Boyle's law and Charles law both, the amount of gas is fixed. We are in both the cases talking about fixed amount of gas, means your n, small n, is also a constant. So here again for the Charles law, we talk about constant pressure and a fixed amount of gas. Constant pressure in n. So here again fixed. So now here what we have is, it states that what Charles found was, as volume increases, your temperature actually increases. Sorry. As volume increases, temperature also increases. But there was now again, let me tell you, all these laws were obtained after doing a set of observations from the experiments. So they have been derived from the experiments directly. What happened was, they found, Charles found that when volume, say initially, say the volume was V naught, okay. Now after, say, increasing the temperature, because if you're finding out the relationship between V and T, you will vary the other value to note down the volume. So if temperature was increased, now when the temperature was increased, it was found that the volume is also increasing. But how is it increasing? There different sets were noted, and then the relationship that came up was that the final volume after increase of temperature by T degree Celsius was T upon 273.15. Stop writing and look onto the board first, because this is like a simple concept that I want you to understand. क्या लिया? Initially volume V naught लिया of the gas. Now temperature was increased and the pressure was maintained constant. So we fix our piston. This is our container. How can we maintain the pressure? We'll just fix our piston. So pressure will remain constant. This is how pressure can be easily maintained constant. अब इसको ना ऊपर करेंगे ना नीचे करेंगे, pressure will not get altered. Now what we are doing is, in order to now observe the volume, we will now increase the temperature. Now when we increase the temperature, in this case, we note down that the volume V naught that was initially there gets increased by a factor of T, which was in degree Celsius. Say I increased it by T degree Celsius. T upon 273.15 times V naught. Do you get it? Initial volume plus this factor gave you the new volume after rise in temperature. Clear with that? Now what happens? Keep looking, no need to write. I'll give you time to write. This Vt can now be written as V naught into 1 plus, I'm just shortening it up, that will be upon T divided by 273.15 into V naught. Now let this, so now here let this be the initial temperature, 273.15, because now there was a need to introduce a new temperature scale. We had taken the temperature in degree Celsius. Charles had taken the temperature at degree Celsius. Here he noted down that there was a need for a new temperature scale which could have been taken, because one thing that is noted is that with increase in temperature, volume is increasing linearly. Linear increase hai, so volume is increasing linearly according to this relationship. And what is the factor that it is getting increased by? It is getting increased by a factor of T upon 1 upon 273 times your V naught. 1 upon 273 times your V naught whenever you are increasing it by T degree Celsius. Okay, so now here this 273.15 was then taken as the initial temperature, which is your T naught, and 273.15 plus T was taken as your final temperature, that is your TT. This TT is now taken in Kelvin. Got it? And when we take up this relationship, we get Vt is equal to V naught into T at T divided by T naught. Right? Which clearly states that Vt by Tt is equal to V naught by T naught, which clearly implies that your V by T is equal to a constant, which implies that V is directly proportional to T is your Charles law. And this temperature is the temperature in Kelvin. I repeat the entire story again. Charles had done the experiment by maintaining the pressure as constant. And what did he do? He used the two variables, volume and temperature. So now on increase of temperature, he found that the volume also increases linearly according to the relationship. What was that relationship? Vt, the new volume, is equal to V naught plus T upon 273.15 times V naught. Okay, when we rearrange that equation, we see that if 0 degree Celsius was our initial temperature, let's take the initial temperature as 273.15. Then it was found that the numerator, if it is taken as 273.15 plus T, we are now introducing a new temperature scale here. The new temperature scale is nothing but where we are taking the initial 0 of the temperature as 273.15 and we are taking the temperature in Kelvin to be equal to that 0 plus the temperature in degree Celsius. So this introduces our Kelvin scale, right? And from here we get our Kelvin scale as temperature in Kelvin is nothing but whatever temperature you have in degree Celsius plus 273.15. So you get it that the temperature in Kelvin actually came up from such laws. Yes.
And if we fix the piston, then pressure as well as volume will be fixed.
No, then in that case you allow it to be flexible in the region which is there. You will keep the volume of the gas already low in that region. See, if initially volume was this, say the volume of the gas is this much, alright, you will leave sufficient scope of the volume to expand. So you will just fill it with vacuum.
Before Charles law, he told that Pk equals to T plus 273.5. Before doing this experiment.
No. This relationship is like whatever the new volume came up. In each of the cases, because he increased the temperature by T degree Celsius, then again he will increase it by another temperature, then again he will increase it by another. So it was a general trend that was observed.
We know the relation between Tk and Tc. Before doing this
No. This factor of 273.15 came up. क्या आप फाइंड आउट करोगे कि एक्चुअली में कितना इंक्रीज हो रहा है, फिर उसको V नॉट से रिलेट किया तो V नॉट को बाहर निकाल लिया. So then he got this factor here, alright, and then when he introduced this factor here, T upon 273.15, then he rearranged it to get this new temperature scale. Any doubts here? So simply remember that the temperature in Kelvin was like taken up here. So now this temperature is also known as the Kelvin temperature, or I mean the temperature in Kelvin is known, this temperature is also known as the Kelvin temperature, or it is also known as the thermodynamic scale temperature or the absolute scale. The Kelvin scale is known as also the thermodynamic scale and the
Absolute temperatures.
it is either known as the thermodynamic scale, the Kelvin scale is known as the thermodynamic scale, and it is also known as the absolute scale. So remember that whenever you have such terms introduced, they are related to your zero temperature or the Kelvin scale. Thermodynamics, I hope you know the meaning. There are two types of forces. It's like a dynamic force or a static force. Dynamic matlab whatever is moving is like your dynamics that you talk about. Static is like stationary. And thermo is again your heat. So whatever changes or movements are brought about because of heat is your thermodynamic scale. So Charles' law was now reduced down to a simple law that stated that your volume is directly proportional to the temperature in Kelvin. Volume is directly proportional to the temperature in Kelvin, and this is what you remember by and large, right? That at a constant pressure and for a fixed amount of gas, your volume is directly proportional to temperature in Kelvin. So if you are plotting a graph, simple one, if you are plotting a graph between say now volume and temperature, now what will that be? say V is equal to K2T now. This is the second law that we are doing, so I'm just putting the subscript as 2. V is equal to K2T. Now this is again Y is equal to mx. If I'm plotting a graph of volume and temperature in Kelvin, so then in that case it will be something like, please explain the VT formula again. What is T here? The initial temperature or the increased temperature? T is the increased temperature. Ma'am, please explain new temperature scale again. Okay, now see, I am just telling you that Charles performed an experiment at a constant pressure. Alright, what did he change? He changed the temperature and he found that the volume was increasing. Matlab, as temperature was increasing, volume was also increasing. He noted that if the initial volume was V0, on increasing the temperature, the new volume was found to increase by some factor, and that factor was T upon 273.15 times your V0. This temperature, small t, is in degrees Celsius. This was the increase in temperature that was brought about by Charles. Then when we mathematically just simplify or rearrange the equation further, we see that this becomes 1 upon T plus 273.15, the whole into V0, right? This is nothing but equal to 273.15 plus T upon 273.15, the whole times V0. So that means that the final volume was related to your V0 in this fashion. That means your final volume was dependent upon your initial volume, but there was an increase by when you multiply your V0 with this factor. So your final volume was an increased volume. Here it was realized that there was a need to introduce a new temperature scale, wherein you had started from 0 degrees Celsius. So your 0 degrees Celsius could have been taken as this temperature, that is 273.15. So we name it as, say, T0. That was the initial temperature. We took the initial temperature as 0 degrees Celsius. Now let the final increase in temperature, because we increase the temperature from a particular temperature to a final temperature. बात समझ में आ रही है? जो भी initial temperature चार्ल्स ने लिया, उस इनिशियल टेम्परेचर को मान लिया, एंड उसने जो भी टेम्परेचर लिया उस इनिशियल टेम्परेचर को मान लिया 273.15, एंड ही टेकन 0 डिग्री सेल्सियस बाय डिफॉल्ट. सो देन ही फाउंड दैट द न्यू राइज, आई मीन जितना भी इंक्रीज हुआ, दैट वाज 273.15 प्लस द टेम्परेचर इन डिग्री सेल्सियस, एंड दैट टेम्परेचर ही नेम्ड इट एज TT. Alright, and this introduced a new temperature scale, that was the Kelvin scale, that your temperature in Kelvin is equal to your temperature in degree Celsius plus 273.15, which is like the initial temperature T0. And when we further talk about this relationship, you get Vt by V0. I am getting V0 to this side, so in the denominator will be equal to T by T0. So there is like a direct relationship. Vt by V0 is equal to Tt by T0. So the Charles law was just summarized as the volume of the gas is directly proportional to the Kelvin temperature of the gas. Is directly proportional to the temperature in Kelvin. And this Kelvin scale is also known as the thermodynamic scale, or it is known as the absolute scale. And whenever you plot a graph between V versus T, you know it will be a straight line passing through the origin. And then because we've done Boyle's law in detail, so I am not explaining each and every plot again. So with this I summarize the Charles law also. Charles law done. I repeat the Charles law because we have to do it again as per a doubt has come. It is that at constant pressure, the volume of the gas is directly proportional to the temperature in Kelvin. And you can also state that the volume increases linearly along when your temperature is in degree Celsius by a factor of T upon 273.15 times V0. Okay, there can be another plot if you talk about the plot of V versus temperature in degree Celsius. You could have also drawn a plot of say V, plot a graph between V See, volume, we are keeping the pressure constant, means there is one way of keeping the pressure constant. I have given you a volume, say initial volume was say around 2 ml of the gas. Okay, now that 2 ml I can take up in a big vessel. Alright, so I am just leaving that 2 ml there and maintaining a constant pressure. So pressure can be maintained as a constant while allowing the volume to expand within a particular region of space of the container. So don't worry about that. So you remember that whenever you can keep one variable constant, there will be at least two variables which will be varied. See, in the first case when you were talking about the Boyle's law, when you kept temperature constant, your pressure and volume were variables. Now you are keeping pressure constant, so your volume and temperature are the variables. Now, if I am asking you to plot a graph between volume and temperature in degrees Celsius, so then how will this plot look like? Remember that your final volume was equal to V naught plus T upon 273.15 into V naught. So if you take V naught to be inside, so then this will be your T. You are plotting a graph between Vt and T. That is why I have taken T outside. T in degrees Celsius. So it is also again something of the type of y is equal to m into x, because what is your x axis now? Your x axis is now T plus C. So your C will be your initial volume. So your initial volume will be say somewhere here. Now with increase in volume, your temperature is increasing. Clear with this? So here the intercept will be your V naught. V naught. This will be your V naught, and your slope will be equal to V naught upon 273.15, and it is a positive slope, so I have just given it a positive. And it is a linear slope. And let me just tell you, when you back extrapolate it, इसको अगर हम further extrapolate करें, whatever is the dotted lines, so when you further extrapolate it, it will reach down to a temperature of 273.15 minus 273.15 Kelvin, which is like kind of a hypothetical case, because here you are talking about the zero volume of the gas. ये वाला origin से इसलिए start नहीं होगा because if you check out the mathematical relationship in itself, तो इसके पास एक intercept पहले से ही है. So आप पहली volume क्या लोगे? V naught, जिस पे आप temperature note करोगे, and that temperature is the initial temperature that you started off with. So that is why. Here what is this? This will be minus 275.3 degrees Celsius. Sorry, just look up here. What is this V naught at 0 degrees Celsius? And what is your 0 degrees Celsius? Minus that is 273.15 Kelvin. So your V naught is taken at initial temperature T naught. Now the entire thing going again. But ये एक सिंपल बात है, चाहे ये पूरी स्टोरी even if you have not understood, you can at least remember how to plot the graphs from the basic expressions. Your basic expression, one of them was V is equal to K2T, alright, and if V is equal to K2T, you know that volume is directly proportional to T, and here you will get a straight line passing through the origin. Another will be like, now here in this case you have volume now to be plotted against T in degree Celsius, तो ये वाला expression याद रखना है, और ये वाले expression में you have an intercept. You getting the point? So in that case you have to remember the plots as per the expression that you have mathematically. So remember that at what happens if I've plotted this graph for T degrees Celsius, what we have is at 0 Kelvin you have volume to be going almost to be equal to 0, which implies that the gases cease to exist. Doesn't it? अगर 0 Kelvin है तो at that temperature I am talking about the volume of the gas to be equal to 0, and if volume of the gas is equal to 0, that means I am talking about some kind of a liquefaction where the gas is not existing at all. So here remember that when the temperature decreases, this is what we understand, that gases start liquefying, and this also comes in from here. That is why majority of the gases start liquefying. And here at one thing that you can remember is that I just introduced you to absolute zero temperature. Absolute zero temperature, you can just note down, is that hypothetical temperature. Hypothetical is something that cannot be achieved, it's just imaginary. Absolute zero temperature is that hypothetical lowest temperature where volume of the gas is equal to 0, where gases are expected to occupy a 0 volume. So Charles' law was like after doing Boyle's law in detail. See, now there is a question, that is why is that increasing factor V upon 273.15. Now this is an experimental observation that it was noted that when you have the volume that was noted with increasing T degrees Celsius of temperature, it was noted that initial volume jitna bhi tha, that increased by an additional amount of T upon 273.15 into V naught. So that is why this factor was totally an experimental observation that came up. And also remember, why did I take V inside and T outside? Was the only purpose for taking that was I was asking you to plot a graph between volume and temperature in degrees Celsius. If you are plotting a graph between volume and temperature in degrees Celsius, it is y versus x. So I am taking this to be y, so I should be taking this to be x. तो इसीलिए मैंने इसको टेम्परेरीली बाहर लिखा था और V नॉट को अंदर लिया था. सो व्हाट डिड आई गेट हियर? T. So this is y versus x now. And what is this kind of a relationship? You know all the mathematical relationships. So this is equal to y is equal to mx plus c. And what will be your slope now? That means there will be an intercept. Your intercept will be equal to your V naught, and it will be a straight line with a positive slope, where your slope will be equal to V naught upon 273.15. Okay? Why V and T temperature graph is taken from the origin? We had seen that from this relationship we had directly come to a relationship that if volume of the gas is varying linearly with the temperature in degrees Celsius, we had seen that the volume of the gas is directly proportional to temperature taken in Kelvin. Okay, that now you know how. Because there was an increase and then there was rearrangement and then T naught was taken, the temperature at 0 degrees Celsius, which is equal to 273.15 Kelvin, and absolute zero temperature is the lowest hypothetical temperature where the volume is of the gas is 0, or gases are supposed to occupy a 0 volume. So if volume is directly proportional to temperature, then in that case volume of the gas can be written as K2T. Alright, and when you plot this is like y is equal to simply mx. तो इसमें intercept है ही नहीं. So that is why when we plot volume versus temperature now, then in that case I get a straight line passing through the origin क्योंकि intercept नहीं है. Okay, this is like a relationship between your expression and your mathematical understanding. So it will be like, in this case it is passing through the origin. Okay, now we move on. Done with that also. Now we move on to the next law, which is the Gay-Lussac's law. We talk about the Gay-Lussac's law of constant constant volume. Temperature constant for Boyle's law, pressure constant for Charles law, and Gay-Lussac's law में you have constant volume and fixed amount of gas. Fixed amount of gas means your N is also the same. Now here, in this case, I mean, alright, for Charles law, one more thing. Whenever you plot a graph while keeping the pressure constant, it is known as an isobar. Please remember that also. When in case of Boyle's law, whatever graphs or plots we had plotted, we call them isotherm. Therm means temperature. Now in case of pressure, they are known as isobar, means constant pressure curves are known as isobars. Now for the case of Gay-Lussac's law, I am asking you to keep volume as constant. Now remember again here in this case, if volume is constant, what are the two variables that we look at? Pressure and temperature. And here again, the pressure similarly, temperature in Kelvin. And it is just the same relationship. Let me tell you, Gay-Lussac also found that the pressure, now I am not repeating the entire thing again, that I have done it in details for the Charles law. Pressure also, the final pressure because now how P and T will be observed, it is easy to increase the temperature, so temperature is increased and then it is observed what happens to the pressure. So in this case, you know, when the temperature will be increased, the kinetic energy of the molecules will increase, and if the kinetic energy will increase, they will collide rapidly with the walls of the container. और मैंने बोला अगर walls of the container के साथ वो ज़्यादा collide करेंगे, then the pressure will increase. So here in this case, the pressure also increases linearly by the same relationship. That was P naught plus, you tell me now, T upon 273.15 in P naught, and this temperature is in degrees Celsius. And again when you rearrange, it was found that the temperature in Kelvin was like absolutely the Kelvin scale was required. And then finally the Gay-Lussac's law also could be given as pressure is directly proportional to the temperature in Kelvin.
Ma'am, but P is directly inversely proportional to 1 upon volume and V is directly proportional to
Temperature.
So it should be P is inversely proportional to 1 upon.
We'll just combine all these laws and just look out as to what kind of a picture does it give, right? So we'll be clubbing in fact all the three together in the end. So we'll see. अगर एक के रिलेशनशिप में दूसरी चीजें देखोगे तो एक ही तीनों में देखना पड़ेगा, तो वो उस एक को पकड़ेंगे पहले and then we'll just compare all the rest of the variables with it. So now here we have P is equal to then is equal to K3 into T. Let me just give you another question then. Now you will tell me what will this graph, temperature is in Kelvin, what will this graph look like? It will be a straight line. This is right. It will be passing through the origin. So this is wrong. So you will have a straight line passing through the origin. This will be the graph, correct? For Gay-Lussac's law. And this will be known as, now this is at constant volume. So this means that this will be known as isochore. Okay. So now here in this case, okay, V4, V3, V2, V1. Now, order. Do you want me to put 4 options for you? Yes? You can just think about the order directly. V4 less than V3 less than V2 less than V1. Okay, first option. Second option, V4 greater than V3 less than V2 greater than V1. Next option, V4 greater than V3 greater than V2 greater than V1. Last option, I am saving my energy. None of these. Alright, third option. Very good. What is the basis of telling the third option? That means in this case, V4 is greater than V3 is greater than V2 is greater than V1. At a particular pressure, you can check out the temperature ranges. So volume will be the lowest when temperature is like low. Volume will be the lowest and then you can just relate it to the Charles law now. ठीक है? तो ये तो now they are like interrelated. तो ऐसे वाले क्वेश्चंस बहुत ज़्यादा आते हैं कि टेल द ऑर्डर ऑफ द टेम्परेचर, वॉल्यूम, प्रेशर. सो यू जस्ट हैव टू अप्लाई लॉजिक देयर. सो डू नॉट गेट पैनिकी if P is inversely proportional to V. Your question. And V is directly proportional to T. Then how is P directly proportional to T? Question mark, question mark, question mark, question mark, question mark. So many question marks. So we'll just see as to how these all are like related to one another. सबसे पहले तो let me just tell you three scientists. What are the names? Boyle, Charles, and Lussac. With a lot of respect. Right? Now all these three scientists had done their experiments independently. So when Boyle had done his experiment, he kept the temperature constant. When Charles had done his experiment, he kept the pressure constant. And when Gay-Lussac had done his experiment, he kept the volume constant. So each of their observations were independent of what the others had done. So they had not clubbed it all together. Got it? So they did not actually question it, but rather they actually find out whatever were the findings, whether they were correct or not. So what did we do? When we talk about a quick recap, when we talk about Boyle's law, we found that at constant temperature, our pressure is inversely proportional to volume. Then we did our Charles law. In this we found that our volume was directly proportional to temperature. Then, very good, temperature in Kelvin is very important. Then we have the Gay-Lussac's law. Gay-Lussac's law mein what we have is like pressure is directly proportional to temperature. Temperature in Kelvin. Now here we have now seen this question also in details as to how to find out the different volumes. So now let us now club it together. There's a lot of requirement coming in as a query. In all these cases, how do you club it together? Is like you can have another one law, which is the Avogadro's law. Now we can talk about the Avogadro's law. In Avogadro's law, you have equal volumes. You can just note it down that equal volumes of all the gases, equal volumes of all gases under same conditions of temperature and pressure contains equal number of molecules. I repeat your Avogadro's law before we move on to the final ideal gas law equation. Avogadro's law, it says that equal volumes of all the gases under ideal conditions of temperature and under similar conditions of pressure and temperature will contain equal number of molecules. Means that if you keep your pressure and temperature constant now, then your volume will be directly proportional to the number of molecules. I repeat it again. Avogadro's law states that equal volumes of all the gases under conditions of constant pressure and temperature contain equal number of molecules. That is, B is directly proportional to N. So here I can say that V is equal to K4 times N. And from here again V is equal to K4 N means it is, what is this N? It is the amount of gas, that is number of moles. What is your number of moles? Given mass upon molar mass, right? This is equal to given mass upon molar mass. This implies that molar mass is a constant generally for a particular system, carbon dioxide, nitrogen dioxide, any gas. So molar mass is equal to therefore K4 into M upon V. And what is your M by V? That is your K4 into D. So again we got a relationship that your molar mass will be directly related to the density of the system. Molar mass is directly related to the density of the system. And now that we've talked about another law, we've added another law to our kitty, and what is that one? Avogadro's law. Simple laws. In Avogadro's law, now we have volume directly proportional to N. Here what was constant? T, and let's note down the constant factors. Temperature and a fixed amount. Then here pressure and fixed amount. Here volume and fixed amount. And here you have pressure and temperature. And remember that a gas which follows all these laws is known as an ideal gas. Normally it is very difficult to observe or obtain ideal gases. Whatever gases you have around you are very much real. There is no ideal case as such. Only at certain ranges of temperature and pressure it is that the real gases, it is noted that your real gases behave ideally. And please remember that conditions asked almost in all the examinations, that real gases behave ideally under conditions of low pressure and high temperature. Gases behave ideally at low pressures and high temperatures. Please repeat it at least 4 to 5 times so that you remember it here itself. And remember that in ideal gases it is actually assumed that intermolecular forces are not present. Each of your gaseous molecules is considered to be an independent moiety. Remember that in cases of ideal gases, each of the gas molecules is assumed to be moving independently. How is pressure related directly to temperature is what we had seen in the Gay-Lussac's law when we keep our volume as a constant. Okay, now we have seen that what is our Boyle's law? It is V. This implies what is our Boyle's law? This is what we've done in today's class. We haven't done anything which is like big and very tough. It's like very simple chemistry. We are talking about gases. These are those states of matter in which thermal energy is very, very high. Compressibility is very, very high. Density is very, very low. Now here we have seen that ideal gases will be those which will follow all these laws. All these laws. What are those laws? Boyle's law. Now Boyle's law states that at constant temperature, revision for all of you, constant temperature, pressure is inversely proportional to volume. Which means that volume is inversely proportional to pressure. Right? For the next we have, for Charle's law, we have already volume is directly proportional to temperature. Right? And then let me just take the third law. 3 laws will help me in getting to the final. Now here in Gay-Lussac's law, what we have is when you, or you can take the Avogadro's law in which you keep volume as, pressure and temperature as constant, what you get, volume is directly proportional to N. So when we combine all these laws, what we get is? What we get is V is directly proportional to, what is that? It is NT upon P. Alright, so this implies PV is directly proportional to N into T, and when you remove this proportionality sign you get your R. So that is equal to PV is equal to nRT. You are very much enthusiastic to talk about R. So, R doesn't stand for my initials alone, but it is also your universal gas constant, and value of which needs to be remembered. Remember that how is this R obtained? The constant value is obtained only under the conditions of STP. So 8.314 joules per Kelvin per mole that you remember is because of this factor of your R is what? R is equal to PV upon NT. Right? So at STP you know that your pressure will be equal to 1 bar, which is 10 to the power 5 pascals, into volume. What is the volume at STP? That is 22.71 into 10 to the power minus 3 meter cube. I am just telling you that these are the units which were taken. N is like your 1 mole. It will be 1 mole. And your temperature is 273.15 Kelvin. And on substituting all these values, you get R to be equal to 8.314 joules per Kelvin per mole, or joule Kelvin inverse mole inverse, which is also equal to, if I just convert this joules into ergs, then I have to multiply it by a factor of 10 to the power 7. So let me just put this R now in different units. R, which is very important for you, it's the universal gas constant, is 8.314 joule per Kelvin per mole. Alright. Then this can also be written as 8.314 into 10 to the power 7 ergs per Kelvin per mole. All right. This can also be written as remember that joules can also be written as you have this 0.082 liter atmosphere, because when you convert your joule per Kelvin into liter atmosphere, this is how it becomes. So liter atmosphere or liter bar, what you have is liter atmosphere mole per Kelvin, or per Kelvin per mole, one and the same thing. So remember that liter atmosphere or liter bar means one and the same. And then you have another value of R, which is 1.987 or 2. For numericals, you can also take it as 2 calories per Kelvin per mole. Calories per mole per Kelvin. R का value देख रहे हैं. We got, once you get it in 1 units, you can always convert it to other units. It is 8.314 joules per Kelvin per mole, or it is 8.314 into 10 to the power 7 ergs per Kelvin per mole. That's like simple. Then when you convert your joules to liter atmosphere here, then it becomes 0.082 liter atmosphere, or it can also be called as liter bar per mole per Kelvin, and it is also equal to 2 calories per Kelvin per mole. Okay. So remember that here what we have is we talk about the ideal gas law equation now, and your ideal gas law equation is very simple. What is your ideal gas law equation? PV is equal to nRT. For all those of you who I just don't expect anyone to get, but still if you got messed up, listen carefully. Remember the ideal gas law equation and you can remember all the laws from it. What is your ideal gas law equation? PV is equal to nRT. Now, Boyle's law. Boyle's law में you keep temperature as constant. ये nR constant है ही है, fixed amount है तो. So Boyle's law is PV is equal to a constant. This is your Boyle's law. Then you talk about Charles law. Charles law में you have pressure and N constant. So if you have your pressure and N constant, then volume is directly proportional to T. And then also if you are saying V by T is a constant, then remember that in that case V1 by T1 will be equal to V2 by T2. Okay, clear with that? And then when we talk about now the Gay-Lussac's law, in Gay-Lussac's law what you have is you have volume and number of the fixed amount constant. So volume in N constant means your pressure is directly proportional to temperature now. So that means P by T is a constant. That means P1 by T1 is equal to P2 by T2. Then last you have in Avogadro's law, you have pressure and temperature constant. So you have V directly proportional to N, which is the amount of gas. So equal volumes will contain equal number of molecules. So with this, we complete today's class with all the laws of the gaseous state. And remember that all those gases which follow all these laws are known as the ideal gases. Those gases which deviate from ideality are known as the real gases. Majority of the gases around you are real gases. When will they behave ideally? At low pressures and high temperatures. Alright, please remember all these laws, and then we'll discuss numericals based on them and move a step ahead. There's one more law that we can just do before leaving up, and that is the Graham's law of diffusion. ठीक है, ये भी एक law कर लेते हैं so that we move on with the applications next time. Graham's law of diffusion, I'm just putting up the name, the last one. Graham's law of diffusion, and this is from where we'll begin next time. Alright. Graham's law of diffusion is nothing but it states that the rate of diffusion of the gases is inversely proportional to the square root of their densities, which is also inversely proportional to the square root of their molar masses. Remember, inversely ka matlab, if one is coming in the numerator, the other will come in the denominator, the other factor. So the rates of diffusion of the gases is inversely proportional to the square root of the densities, and also to the rates are also inversely proportional to the square root of their molar masses. Another important thing that I want to draw your attention to is like, what is your diffusion? Diffusion is like some tendency to distribute itself uniformly. Diffusion means directly passing through into something and it just diffuses. Alright. Another important term here that I want you to be familiar with is effusion. And effusion is movement of the gas through small whole when actually there is some kind of a, when subjected to some kind of a pressure. All right, there are two yeah, whenever you have the movement of the gas through a small hole when subjected through some kind of a pressure, all right, it will not automatically move, but if you are actually making it move out of some hole, then in that case you will say it is effusion. And diffusion is like when you're actually that spreading uniformly of the gas, when you have the tendency of a substance to distribute itself uniformly throughout. Clear with it? All right, then all the best. Just go through all these laws and applications and we'll discuss them next time again with further on topics. Thank you.